Okay, so we're finishing up chapter 1. We have 2 more lessons this week, and then we're going to review and have your take your test on chapter 1. So they kind of go together. We're talking about functions, and then once you know what a function is, we can kind of look at graphs of functions. So remember, in one of our last lessons, a relation is just a set of ordered pairs. And usually you get that set of ordered pairs by solving an equation, right? That has an x and a y. So you put a number in for x, it spits out a y, something like that. So a relation is a set of ordered pairs, and they're usually solutions to an equation or some kind of situation in math. A function is just a type of relation, a specific type of relation, and that's whenever none of your x's, none of your domain, none of the independent variables, the numbers that you put in, none of those are repeated. None of those can be repeated in your solution set. Every single time you use a different number for x, it always spits out one corresponding number for y. You never have repeated x values. So what do I mean by that? Here's 2 examples of sets of, or relations, I guess. So it's sets of ordered pairs. So if we look at this first set of ordered pairs, what are all my x values? What's my domain? So I've got a 0, a 2, a 4, and a 6. 0, 2, 4, 6. Are any of those numbers repeated? No, they're all just used once, right? So none of my x's are repeated, so this is a function. So I write, yes, this is a function, and because none of these numbers are repeated, no x's repeated, function. And again, a function is just a specific type of relation. Okay, and then the second one here, we have this set of ordered pairs, this relation, 0, 1, 4, 6, 0, 6, 5, 4. Let's look at all of our x's. We don't really care what the y's are. They can repeat, that's fine. But to determine if something is a function, we're just looking at the x's. And I'll show you in a minute why that works out with the vertical line test. So here our x's are 0, 4, 0, and 5. So the first number in each ordered pair. So do any of those numbers repeat? Yes, they do. So when x is 0, I get 2 different answers for y. When x is 0, y could be 1, or when x is 0, y could be 6. And that's all fine and good, but that just means this is not a function. For every x value, there is one y value, and that's not the case here. So we'll say, yes, 0, repeated. So this is not a function. I went off the page. No, okay, good. I'm like one of those people that underlines everything. I don't know why, it's like a bad habit. Okay, so that's all we're talking, that's literally, it is no more complicated than that. You've got a set of ordered pairs, you've got a relation, do any of the x's repeat? We don't care if the y's repeat, that's fine. They can repeat all day long, but the x's cannot repeat in a function, okay? So if we were going to graph a function, I'll read this first and then show you my graphs. If you draw a vertical line, a straight up and down line, through any place on the graph of a relation, that relation is a function if the vertical line only crosses the graph in one place, okay? So here's 3 kind of different types of graphs. Okay, so for this graph right here, I can draw a vertical line. Do I want to do it in a different color? No, I don't. Yeah, I'll just draw here. I'll draw a dotted line. Any vertical line through any place on my graph. This vertical line only touches my blue graph in one spot, right? I could draw one over here. It only touches that blue, the graph of my relation, in one spot. So because the vertical lines all touch my graph in one spot, this is a function. Okay, for this next graph, any place on the graph, I should be able to draw a vertical line and it only touches my graph in one spot. So if I draw a vertical line here, where does it cross over my blue graph? Here and here. Oh. Okay, well that's not a function. If you draw a vertical line and it touches the graph of your relation in more than one place, then the relation is not a function. And if we think about it, when we come up with the ordered pairs for these two spots where our vertical line crosses the blue, this would be, let's say, like -1 up 2, and this one would be at -1 down 2, or whatever. So they both have the same x value in the front. -1, +2, -1, -2. And if they both have the same x value, it is not a function. That's what we just set up here at the top. Can't have the same x values. So if a relation, when you graph it, has any of the same x values, it's not going to be a function. That's all we're saying. This last graph is kind of a special case. It's a step graph. We don't really graph all those that often, but here it looks like if we were to draw a vertical line through these two dots, it looks like it would cross two places on my graph, right? Except that when this is an open circle, that point is not included in the answers to the graph of this line, right? That's why the circle is open. If it's shaded in like this guy, it's included. So we're going to include this point right here. But up here, it's an open circle, so we are not including this. So if I drew a vertical line down through this, it looks like it would cross through this point and this point, but this point doesn't actually exist, right? And so then people say, well, why did we put a circle there? Well, because the decimal place directly next to it exists, right? 0.0001 places over, that exists, that's part of our solution. But this exact dot itself does not. So to include everything to the right, we go ahead and put a dot here, but to show that the dot itself is not included, we leave it open. So if we were to draw a vertical line, oh, there's the bell. Now we're going to get a tardy bell in a second too, a warning bell and a tardy bell. That's okay. If we were to draw this line down through here, it doesn't actually cross through any point right here, okay? So this actually is a function, not to like beat a dead horse. This little open circle, we'll say open dot, it doesn't count. It looks like it would, but it actually doesn't count. So you're not going to see too many of that, but if you do come into a situation where you have to draw a vertical line and it looks like it's passing through 2 points, but one of the points is an open circle, it's not actually passing through 2 points. Okay, so hopefully that was helpful. Next in this lesson is function notation. So function notation is just kind of a funny looking way of writing an equation, right? So in a normal equation, we have a y. In function notation, we just rewrite y as f of x. It's still y. It's still y. There's still a y there. We just don't write the letter y. We write it like this, okay? So if our equation was y equals 2x plus 5, and we picked a number and put it in place for x, we would simplify this and it would spit out a number for y, right? Well, that's a function. That means y is a function of x. Whatever we put in for x is going to spit out a y. Y depends on x. So when we write it in function notation, we write it over here. Y is a function of x, right? Whatever x is, y is a function of that. Y is like a result of that, okay? So what do I mean by that? If I were to use this equation and say, what is y when x equals 2? I would just plug in a 2 for x. 2 times 2 is 4. 4 plus 5 is 9. Y equals 9, right? It's the same exact thing. We're not changing the math. It's the same thing. It's just the notation. Sorry, there's the warning bell. It's just the notation. So a function of 2, when x is 2, we put the little 2 here. Don't say f of x equals 2 times 2 plus 5. Whatever you're putting in place of x, you got to show that over here. So in this equation, when I put a 2 in for x, this equation is going to become a function of 2 once I simplify it. So 2 times 2 is 4. 4 plus 5 is 9. So a function of 2 in this equation is 9. 9 is the result of putting a 2 in for x. It's the same thing. It's just the way we're writing it. That's it. All right, and then a couple kind of little, I wouldn't say exceptions, but funny looking ways. You can see my writing through the back of this, that's funny. A couple funny looking ways of solving this is instead of just saying put a 3 in for x, they'll give you something like this. And they'll say if your equation y equals -4x plus 7, if we write it in function notation, so we write f of x equals negative 4x plus 7, find f of 3 plus 1. What the heck does that have to do with this, right? This is saying that in this equation, wherever you see an x, you're going to replace it with a 3, and that's going to be your function. And then once you've simplified that, you're going to add 1 to the end of it, right? So we're going to have f of 3 plus 1, and that's going to equal negative 4 times 3 plus 7. That still stays the same. And then on the back of it, we're going to add a 1, right? And then once I simplify that, negative 4 times 3 is negative 12. Negative 12 plus 7 plus 1. Negative 12 plus 7 is negative 5. Negative 5 plus 1 is negative 4. So a function of f of 3 plus 1 on the end is going to equal negative 4. That's all that's saying. We're just simplifying. That's it. That's our solution. Okay? Same equation. If we took the exact same equation, the same function, and then we said find f of, and then everything is inside parentheses, right? Up here, the 1's not inside parentheses. It's outside. So it doesn't have anything to do with the function. We're just tacking a 1 on at the end of the whole thing, adding 1 at the end. This does have to do with the function. Anything inside these parentheses is what we're going to substitute in place of x. So if we rewrote this, we would say f of x plus 2 equals negative 4, and then in place of x, we're going to replace it with x plus 2, and then plus 7. So now I can simplify. And here to simplify, I actually have to distribute that negative 4, right? Negative 4 times x is negative 4x. Negative 4 times positive 2 is negative 8. So now those parentheses are away. And then I still have this plus 7 on the end. So when I simplify that all the way, I get negative 4x minus 1. So a function of x plus 2, meaning we put x plus 2 in place of x, is just going to be negative 4x minus 1. So whatever's inside the function parentheses is what you replace x with. Whatever is outside the function parentheses when you're substituting, that doesn't go in place of x. That just gets tacked on to the end of your equation. Okay, so pretty simple. And then if we looked at the study guide here for functions, again, and it tells us, and I included the study guide on your website, I guess, not your website, the school, I'm trying to do two things at once. The Schoology page, this is what you guys have to fill out. Identify function relations in which the element of the domain is paired with exactly one element of the range. Remember, you cannot repeat x's. So they give you an example here. So if you had 4, 1, 7, negative 2, negative 3, 1, and 6, negative 3, is it a function? Explain. And then they go ahead and do that for you. Since each element of the domain, since each x value is paired with one element of the range, this relation is a function. Each x has its own y. There's no double x's, right? What would not be a function? Not a function. If I had an ordered pair that was like 1, 2, 1, 4, 1, 7, 1, 9, let's say. It doesn't really matter what y is, but all of my x values get repeated. In what situation could you put the same thing in place of x and the same equation spit out 4 different numbers for y? It doesn't make sense, right? It's not going to be a typical situation. So this would not be a function because all of our x values are repeated. That's all you got to worry about. Are the x's repeated? Determine whether 3x minus y equals 6 is a function. Anytime that you have an x and a y, and there's nothing squared or anything, it's going to be a function. Every time, it's going to be a function. Since the equation is in the form ax plus by equals c, anybody remember what form that's called? Standard form. The graph of the equation will be a line as shown. And anytime you have a straight line, it's going to pass the vertical line test unless it's a vertical line itself. Everything else is going to pass the vertical line test. And if it passes that test, then yes, it's a function. And it tells us there that it is. if you draw a vertical line through each value of x, the vertical line passes through just one point of the graph. So the line represents a function, right? We could just draw that and it only crosses through one spot. Okay, so then down at the bottom, you got to draw your vertical lines through everything, right? And I believe this was your assignment. I printed this out to do it with you. Maybe I left the practice, I'm not sure. I'll do a couple of these. If it's your assignment, then you get some freebies, right? Okay, so up here in this first graph, I could draw a vertical line through any place on this graph, and it's only going to touch one of my ordered pairs. It doesn't matter what the graph looks like. It doesn't have to be a pretty straight line. It doesn't have to be a pretty parabola or anything like that. It still has to pass the vertical line test to be a function. So yes, this is a function. Number 2, if I draw vertical lines, yeah, it's only going to touch my parabola in one spot, each vertical line. So that's going to be a yes. What about this guy? Do any of my x's repeat? Well, these are all my x's. We don't really even care about this side. We don't care. We only care about what the x's are. And yes, look at -1. There are 2 different lines coming from -1. That means one of our ordered pairs is -1, 4, and one of our ordered pairs is -1, 5, and that's not going to work. We can't repeat. So this is no. This is not a function. So you just have to finish looking at everything and figure out for every value I put in for x, it should only spit out one y, right? Okay, x squared plus y squared equals 8. X squared plus y squared equals 8. Since we're squaring this, this is actually going to end up not being a function, because since both of these are squared, not just one of them, but both of these are squared, if I put in a, let's say a 2 for x, 2 squared is 2 squared plus y squared equals 8. If x is 2, what does y have to be? Well, then that would be 4 plus y squared equals 8. Minus 4 on both sides, y squared would have to equal 8. But since it's y squared, that means y could either be positive 2 or negative 2. So 2 solutions to this equation are 2 negative 2 and 2 positive 2. There's other solutions too, but that's just 2 of them. And since my x value gets repeated with 2 different values of y, this is not a function. You can't get 2 different y's for the same x. It's 1-to-1. Each one x has a different y. That's it. Negatives don't count. -2 and +2 are not the same answer. So if you see x's like this and one's negative and one's positive, they're different. That would be a function. That's different. It has to be the exact same number, sign, and everything. Okay, and then on the back side of this, we have our function notation again. It tells you up at the top. I love these study guides because it re-teaches you the lesson. Function notation is when we write f of x. Excuse me. So like here's some examples. F of x equals 3x minus 4. Find f of 3. So we literally just put a 3 in place of x. 3 times 3 minus 4. 9 minus 4 is 5. So we would say f of 3 equals 5. That would be our solution. B, same thing. We put a -2 in for x. 3 times -2 minus 4. -6 minus 4 is -10. So a function of -2 in that equation is -10. That's our result. So that's all we're doing down here. The one thing you need to pay attention to, they like to give you a lot of these, and I don't really know why, is they give you 2 different situations. So one says f of x and one says g of x. What I do when I solve is I make them look different. So all the f of x's, I'm going to highlight. And then in my questions down here, if it says f of x, that's the equation I'm using. This one says g of x. So I'm not using the f of x function. I'm going to use the g of x function, right, with that one. This one's f. So I'm going to use f. This one's f. This one's f. This one's f. This one, this one, this one, this one. So anything that starts with an f, I'm using with the f function. Anything that starts with a g, I'm using with the g function. So it's kind of like 2 different things going on. This highlighted equation has nothing to do with number 2. You don't look at it, just ignore it. Number 2, you're just looking at this guy. All right, so hopefully that makes sense. All right, secondly, that was all of lesson 1-7. Excuse me. Secondly, we want to analyze or kind of interpret the graphs of these functions. So we're not just looking at any graph. We're not looking at graphs of all relations. We're just looking at functions. So we already know that every single graph we're about to look at passes the vertical line test. It's a function, right? So there's a few different things, I think like 7 maybe overall, that you have to think about when you're analyzing or interpreting the graph of a function. First thing is your graph linear or nonlinear? Linear obviously means it's in a straight line. Nonlinear is anything else. If there's any curves to it whatsoever, it's not a straight line, that's nonlinear. So that's the first thing you can kind of look at and determine. The second thing is the x and y intercepts. You can figure out, where does my graph cross, excuse me, where does my graph cross the x-axis and where does it cross the y-axis? I could use the same graph here, it doesn't really matter. But for this parabola here, it crosses the x-axis here and here. So that's -3, 0 and +3, 0. And it crosses the y-axis right here, so that would be 0, -3. I didn't write that down, but that's where the y-intercept would be. On this equation, for this guy, it looks like it crosses the x-axis kind of in between two, so maybe like -1.5. And then it crosses the y-axis at 0, -2. So this is, I've just wrote out just the x-intercepts here as an example of the x-intercepts when you're looking for that. And here, this graph I used as an example of y-intercepts. This is where it crosses the y-axis. Y goes up and down, x goes side to side. Think of it like y has a long tail. It stretches down long, up and down long. X is just like short and fat, like side to side. Okay, next thing we want to look at is whether or not the graph has line symmetry. Line symmetry just means you should be able to fold it in half down the vertical line. Can't fold it in half down a horizontal because it's a function. So if you folded it in half down a horizontal line, it should not meet up, right? It can't meet up because it's a function. But if you fold it in half along a vertical line, it should meet up perfectly, right? I kind of did a dotted line here, but it didn't show out when it printed, so I highlighted it. But you can see that this vertical line is about 4 units away from this side of my graph, and it's about 4 units away from this side of my graph on the x-axis, right? It's the same size. So if I folded this in half along this line, they would meet up. So this is line symmetry, and we call this line that we folded on the line of symmetry. So in general, the graph has line symmetry. You can fold it in half. Where can you fold it in half? This line, which is the line of symmetry, and it looks like it's at about x equals 2. So the line of symmetry goes through x equals 2, all right? What about this graph? It's a straight line. Can I fold it in half? No. If I folded this in half anywhere, the top part would like end up going this way, right? And it wouldn't meet up. It doesn't work. So whenever you have a straight line like this, it does not have line symmetry. This graph does not have line symmetry, it says. If I haven't put this document up already, I'll put it up for you. It's like a quick cheat sheet kind of thing. There's nothing to fill out on it. It tells you exactly what all these things are. Okay? Fourth thing we have to look at is positive and negative. What the heck does that mean? When you're looking at a graph, the positive portion of the graph is everything above the x-axis, and the negative portion of the graph is everything below the x-axis, right? So if the x-axis were water, everything positive is everything up above water. You can breathe, that's a positive, right? So everything up above water. So I took the x-axis and everything above it, and I split it up here. So everything up above the x-axis is this little portion and this little portion. And then everything negative is everything below the x-axis. That's bad, right? If you're underwater, you can't breathe. That's negative. So everything below here is negative. So how do we represent that? We have to say what portion of our graph is above and which portion of our graph is below the x-axis. Since we're talking about the x-axis, we just use the x value. So here, everything above the x-axis when x is anywhere in between -4 and 0. It could be -3, -2, -1. It could be one of the decimal points in between there. But if x is any number, -4 to 0, our graph is up above the x-axis, right? To get to any of these points, I'd have to go up. I'd have to go, or stay on the line, right? I guess we wouldn't actually include, oh, that's a good point. We wouldn't actually include, that's why there's not a line underneath here. We don't actually include points on the line, but everything between them. If it's on the line, it's not positive or negative. It's got to be above or below the line. So we don't include -4 and 0, but everything between is included. So to get to, let's say, this point, I'd have to go backwards 2, up 2 to get to that. So anything I have to go up for is positive. So when x is in between -4 and 0, my graph is positive. Also, when x is anything bigger than 4, right? I get to 4, my graph, I can't see my graph here, but once I get to 4, when x is 4, I'm on the x-axis, and then anything bigger than that, as I go right on my x-axis, my graph starts to go up. And it never changes direction again, which tells me it just keeps going on and on forever. So as long as x is greater than 4, not equal to 4, but just greater than 4, my graph is going to be positive. When I look at the negative side, same thing. Which portions of my graph are negative? Well, my graph goes down. Now, I always read my graph from left to right, always. I'm always going from left to right. But this portion of my graph is below the x-axis, right? So if x is -4, it's on the x-axis, but if it's anything smaller than -4, anything to the left of this number line, it's below the x-axis. So when x is less than -4, my graph goes under the x-axis. It also goes under the x-axis when x is in between 0 and +4. So when x is bigger than 0 but less than 4, in here, anywhere in between here, my graph goes down below the x-axis. So hopefully that kind of helps you. Go back to this, look at how I kind of wrote it out. You're just telling me what is x when your graph is above the x-axis, what is your x value when x is below the x-axis. A couple more things. All right, then we have increasing and decreasing. So this is a fun one. All you have to do is when we're reading every single time we read a graph, left to right, you're gonna think of it as a roller coaster, right? So you're here, left to right, we start here on the end. Now we know the end keeps going, but the portion of the graph we're looking at, that's all we're interpreting, is what we're looking at. So if we start here, we start going up, right? If you're on this roller coaster cart, you're going up, 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 up. And to me, that's going to tell me I'm going to fall down in a second. But I know I'm going up. So this portion, left to right, this portion of my graph is increasing. When do I stop increasing? Right about here at this dot, right? Right here at the top, it levels off. So I'm not going up anymore. I'm staying the same. And then after that, I'm decreasing. If I'm on a roller coaster, I'm going down. Until I get to this point, the lowest point here, and then I go up again. So all of this is increasing. So just think of a roller coaster. When am I going up? When am I going down? Always going from left to right, okay? So how do I represent that? I'm increasing when my x value is anything smaller than this point right here. So what's this point? -2. So when x is anything smaller than -2, and I'm in my roller coaster thing here, I'm going up. X could be -4. At that point, I'm headed up. X could be -3. At that point, I'm still headed up, right? Anything less than -2, I'm headed up. And then also, so then I start going down, but then I start increasing again after +2. Everything's measured off this x-axis, kind of like a number line. So when I'm here, +2 on my x-axis, my graph starts going up. It doesn't start going up at 2, but anything after that starts going 2. So when x is greater than 2, I'm going up again on my roller coaster. So my two portions of my roller coaster that I'm going up at are when x is less than -2, right here, and when x is bigger than 2, right here. Okay, so that leaves the middle. I'm not going up in the middle, right? I'm going down, I'm decreasing. So this portion right here is when I'm going down. So it starts after when x is -2, and it stops when x gets to +2. So when x is anything in between -2 and +2, when my graph is in between those 2 points, it's going down. If I'm less than -2, I'm coming up. If I'm bigger than 2, I'm going up. But if I'm in between -2 and +2, I'm falling down, right? So I'm decreasing when x is in between -2 and +2. X is bigger than -2, but smaller than +2, right in here. Don't overthink it. It's just simple. I'm like talking it to death, sorry. All right, 6, we're almost done. Relative extrema. So those 2 points where I switch directions, those are relative extrema. Why relative? Because when you think of extrema, it's like the extremes, okay? What we're asking is, what's the highest point? What's the lowest point? But there's not just one answer. It doesn't have to do with the entire graph, right? Look at that graph that I used on the front here. This guy. This goes up and down. Oops, this guy. This goes up and down a bunch, right? Up, down, up, down, up, down, up, down. So I'm not just looking for one highest point. I'm looking for the highest point when I change direction. Every single time my graph changes direction, it had to stop, level off, and then go the opposite way, right? So if I'm going up and I stop and I go down, what's the highest point I got to, right? This little dot right here. If I'm going down and I stop and I go back up, what's the lowest point I got to? So those are called relative extrema because they're just relative to that little direction change. There could be other direction changes that have different extreme points. So they're all relative to each other, right? You could have a whole bunch of relative extrema in one graph. So here, we have the same looking kind of graph here. And as I'm going up, 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 when I get to this dot, I stop. That's the highest point when I change directions. The highest point I get to before I go back down on that roller coaster. So that's a relative maximum. That's a relative maximum. So here on my graph, the relative maximum is at -2, +2. And it says it up here above the graph too. And then here, I'm going down, 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 down. I change direction and I go back up. It does not matter how high my graph goes. It can go up forever, right? There's no maximum because it's infinite, it just keeps going. But when I change direction, there was a maximum point. When I change direction here, there was a minimum point. That's what I'm naming. So this guy right here is over 2, down 2. My minimum, 2, -2. It also lists it up here above the graph. Those are my relative extrema. They only occur when you change direction. Changing direction. Only occur when you change direction. Just like on a roller coaster. What's the highest point you get to before you drop and lose all your stomach, right? Okay, number 7, this is the last one. The last thing we can kind of interpret when we're looking at a graph is the end behavior. So it's these 2 ends where we usually see arrows, right? What happens on the ends of our graph? We don't keep seeing graphs, so what do we assume happens based on what we're looking at? So we just want to know what happens to y when x goes up to the right and what happens to y when x goes down to the left. So when x gets bigger, what does y do? Meaning, where does my graph go on the y-axis? I know each point on my graph, the x value is getting bigger as I go this way. So what's the y value doing? So if I'm looking this way, as I get bigger, my graph's going up. I'm climbing up the y-axis. I'm not going down, I'm going up. So as x gets bigger, y gets bigger. As x goes up, y goes up. That's one side of my end behavior. Now I got to look at the other side. You only have 2 sides of your graph, right? The left and the right. So when x gets smaller, as x gets lower and lower and lower, less and less and less, what is the end of my graph doing? Is it going up? No, it's going down, 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 down. The further left I go, the further down my graph goes. So as x goes down, y goes down. That's all in behavior. You literally write it like that. X down, y down. That would be your answer, right? If you were trying to interpret this. X up, y up. That's all you write. Easy, right? And usually you'll see it as x up, y, nothing, x down, y, nothing, and you're supposed to fill in the little arrow, right? So in this case, y would go up. In this case, y would go down. That's all you have to do is fill in the arrow. All right, so let's look at a couple, and this video is getting kind of long, sorry. Let's just look at and analyze or interpret a couple graphs here, okay? So this is my first one. Before I even start looking, I want to start labeling, okay? So I see my intercepts. Right here is one of my x-intercepts. Right here is one of my x-intercepts, right? Where is this point? I had to go backwards 3 up 0. So negative 3, 0. To get to this dot, I had to go forward 3 up 0. I also see this maximum point up here, right? It's the highest point. It's at over 0, up 5. Okay, so that's kind of all I can label. Now remember too that we have the positive and negative, so everything above water, everything below water. I'm gonna use the old paper I have, has writing on it, sorry. So if I cover up everything below water, this is the portion of my graph that's positive. If I cover up everything that's positive, this is the portion of my graph that's negative. So in a second, we're going to analyze that. So I wrote it down on here. I'm going to put this document up for you as well. Intercept. So what's my x-intercept? What's my y-intercepts? My x-intercepts are negative 3, 0 and 3, 0. And my y-intercept, where am I crossing the y-axis? Right at this point, 0, 5. Okay, so there's my intercepts. Is this linear or non-linear? Is this a straight line or not? Not at all. It's a parabola. It's curvy. So this is non-linear. Or I could write non-linear or whatever. I'm going to put parabola. You do not have to write whether it's a parabola or a straight line or whatever. I'm just writing it. All right, then line symmetry. Does this graph have line symmetry? Could I fold it in half, side to side, and the two sides match up as like mirror images of each other? Well, I mean, I stink at drawing. It's not a very good drawing, but if this was drawn correctly, then yes, it's symmetrical, right? I could fold it along the y-axis. It's 3 units this way, 3 units this way. Everything looks symmetrical. So this does have line symmetry. It's mirror images, half and half. So we're going to say yes. And then I could put, what's the line of symmetry here? It's the y-axis. So I could put y-axis, or I could put when x equals 0. You always have to tell where on the x-axis is your line of symmetry. It's the y-axis or when x is 0. That's my line of symmetry. Okay, and then my relative extrema. So this only happens when I'm changing direction. How many times do I change direction here? Well, I'm going up, 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 and then I change and go down, 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 down. So what's the highest point I got to when I change direction? 0, 5. And that's a maximum. It was the highest point I got to. So there is no relative minimum. I never change direction to go back up again, right? There's no relative minimum. But the relative maximum was at 0, 5. You'll see that a lot. You don't have to have one of each. Some you won't have any. If it's a straight line, you're not going to have any relative mins or maxes. It's only when you change direction. We only change direction one time here. So we're only going to have one, either a minimum or a maximum. We would have a minimum if our graph looked like this, right? But since our graph looks like this, we had a maximum. We got to the highest point, not the lowest point. All right, and then positive and negative. Which portion of my graph is above water? Well, looks like anything in between these two dots is up here above the x-axis. So when x is in between -3 and +3, anything in between here, my graph is up above the x-axis. So down here, I'll put it's positive when x is bigger than -3, but smaller than +3. X is in the middle of negative and +3. And then where is it negative? Okay, so then I have to kind of think about it. I got to cover up what's above the x-axis. Okay, so it looks like if x is anything to the left of this dot, my graph is under the x-axis. If x is anything to the right of this dot, it's under. Okay, so this is all negative. So when x is less than -3, if it's anything over here, my graph is below. When x is greater than 3, when x is bigger than 3, to the right of 3, it's below as well. So I'm going to say x is less than -3, x is greater than +3. That's where my graph is, that's where my graph is negative. Then I have increasing and decreasing. So here's your roller coaster, right? My graph is going up, 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 and then I change direction and it goes down, 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 right? So where did I change direction at? 0, 5. So on my x-axis, my graph is going up, 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 up until I get to 0 on the x-axis. Once I get to 0 on the x-axis, my graph turns around and goes back down. As I go this way, my graph's going down. As I go this way, my graph's going down. Or I guess coming up, if I'm reading left to right. My graph's coming up over here till I get to 0, and then after 0, it's going down. So it's increasing as x is less than 0, and then it goes down when x gets greater than 0. It's not doing anything when x is 0 because it's just hanging out up there, right? That's my relative maximum. And then lastly, the end behavior. So I'm looking at this side and this side. So as x gets smaller, what's my graph doing? Is it going up or down? It's going down, right? So as x gets smaller, my graph gets smaller. And then here, as x gets bigger, what's my graph doing? Is it going up or down? Down, right? So as x goes up, my graph, or y, the y value of my graph, goes down. As x goes up, my graph goes down. So for this one, both of these go down. Hopefully that helps you. I think, yeah, we'll just do this one real quick, one more. Just to cut this video off because you've been following along for a while. All right, so we've got this kind of squiggly line. It was on your notes there for a minute. For this squiggly line, first thing I want to do is label everything. So every time I cross the x-axis, I want to label that. Every time I cross the y-axis, I want to label that. And then I also want to label every time I change direction. Okay, so this guy is negative 1, 2, 3, 4, 5, negative 6, 0. This guy is at negative 2, 0. This bottom point is at negative 4, negative 2. This point right here is at over 2, 0. This point is over 4, negative 2. And this dot where I cross the x-axis is over 6, up 0. Okay, so now I can start analyzing. First off, what are my intercepts? What's my x-intercepts? What are my y-intercepts? I can put them down in here. So my x-intercepts, I have 1, 2, 3, 4. My graph crosses the x-axis 4 times. So that is negative 6, 0, negative 2, 0, positive 2, 0, and positive 6, 0. Those are my x-intercepts. What about my y-intercepts? I only cross the y-axis 1 time, and that's this guy right here. So that point was over 0, up 2. 0, 2. There's my y-intercepts. Next is this linear or nonlinear? I think it's pretty obvious it's not a straight line, so this is nonlinear. Okay, does this have line symmetry? Does it have lines? If I fold it in half, does it have line symmetry? I mean, it looks like it does. We'll go with yes for now. It's an infinite squiggle line, so I think we could get to a point where, like, what if I folded it in half right here? Well, I guess it would still meet up. We don't have one line where we fold it in half, but we're gonna say yes for now because it is symmetrical. It is mirror image. We just don't have a line of symmetry. All right, relative extrema, so the minimums and maximums, every time I change direction. So reading from left to right, I'm going down, 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 then I change direction and go up. So the lowest point I hit was negative 4, negative 2. So that's a minimum. Okay, so I hit this point, then I start going up until I get here, and then I change direction and go down again. So the highest point there is 0, 2. That's a maximum. Okay, so I'm at 0, 2. then I start going down, 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 until I change direction. So the lowest point I hit before I change direction is 4, -2. That's a minimum, because it's the lowest point I hit. And then I go up, 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 and then my graph stops. I don't change direction again, right? I mean, I can imagine I probably do, but it doesn't show that, so I don't put anything else. That's it. All right, positive and negative. What portions of my graph are above the x-axis? If I cover up everything below, what portions? Well, it looks like when x is anything smaller than -6, when x is between -2 and 2, and then when x is anything bigger than -6. Right? All of that is above the x-axis. So when positive is when x is anything smaller than -6, when x is in between -2 and +2, it's got to be bigger than -2 but smaller than +2, and then when x is anything bigger than +6. So that's all the parts of my graph that are positive. What about the parts that are negative? If I cover up the top, where are they negative? Yeah, in between -6 and -2, and in between +2 and +6. So when x is, what is it, -6 and -2? It's got to be bigger than -6, but less than -2. And then same thing on the right side when x is in between +2 and +6. Think of it like water. The x-axis is like water. Okay, and then increasing and decreasing. So this is a lot to write as well. All right, so as we read from left and right, we start off decreasing. So we're going down, 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 down until we hit this relative extrema, and then we go back up. So we're decreasing anywhere x is smaller than this point right here, and the x value here is -4. So whenever x is to the left of -4, my graph is going down. I know the arrow is pointing up, but we're reading this from left to right. We're reading it from left to right. So we're coming down here until we get to -4. So when x is less than -4, we're decreasing. Okay? Then from -4 to 0, we're increasing, right? On our x-axis, when we're in between -4 and 0, our graph is going up. So we're increasing when x is in between -4 and 0. We're increasing here. Then we hit a relative extrema, a maximum at 0, and then we start going down again. So in between 0 and what am I going down? In between 0 and +4. Once I get here, this line right here. Once I get to +4, then I start going up again. So I'm decreasing between 0 and 4. So I'm decreasing when x is in between 0 and +4. And then after +4, I start increasing again, and I never stop. My graph stops there, so I'm done. So when x is anything bigger than +4, I'm increasing. When x is greater than 4, I'm increasing. Hopefully, as we look at it and kind of talk through it, it's making sense. In my brain, if I kind of imagine there being like lines here, 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 I can kind of compartmentalize it a little bit, right? So all this is decreasing, all this is decreasing. So anytime x is less than -4, I'm decreasing. Anytime x is in between 0 and 4, I'm decreasing. This other stuff I'm increasing in between -4 and 0, in between 4, and then everything to the right of that, I'm going up. So we're just kind of analyzing that. All right, and then lastly, in behavior. So we're looking at the two ends. So we got this arrow, this arrow. So first off, as x gets bigger, what does my graph do? As x goes to the right, is my graph going up or down? My graph's going up the y-axis. So as x gets bigger, y gets bigger. So as x goes up, y goes up. And then as x goes down, as we go to the left, what direction is my graph going? Is it going down or is it going up? It's going up. I'm climbing up the y-axis again. So as x goes down, y goes up. My two ends are going up. Okay, and then so lastly here for interpreting graphs, it's not all just so much strictly about looking at a graph and telling me where it's going up or down. We actually want to think about a situation that a graph is showing, kind of like a word problem. So that's what we're really analyzing, but you got to understand the graph before you can interpret what it means. So here on the study guide, first thing we have here, it says interpreting intercepts and symmetry. Oh, am I on the wrong side? No, on the right side. Interpreting intercepts and symmetry of a graph. So first thing, the intercepts of a graph are points where the graph crosses an axis, the x and the y-intercepts. And then a graph possesses line symmetry in a line if each half of the graph on either side of the line matches exactly. So it's got to perfectly match up like a mirror image of each other. So that's what we're focused on for this front side. Okay, so I've got this straight line here. They show you this is the y-intercept, this is the x-intercept. That's what we just kind of went over. And then we have a word problem down here. We're going to look at this graph. So it says, architecture. The graph shows a function that approximates the shape of the gateway arch. So this is supposed to be like a bridge, the gateway arch, where x is the distance from the center point in feet and y is the height. So this is important when you know what's being represented on the x-axis and what is being represented on the y-axis. Identify the function as linear or nonlinear, then estimate and interpret the intercepts and describe and interpret any symmetry. So all it's asking us to do here is talk about the intercepts and the symmetry. That's it, okay? And not just what the graph is doing, but okay, then what does that mean if distance is along the bottom of my graph and height is on the side? Okay, so we can look right here and we can see that the y-intercepts tops off up here. This point right here is the highest point. That's where we cross our y-axis. So it looks here on the side like every line is worth 80 feet. Okay, so if this one is, was it 560? The next one would be, plus 80 would be 640. 640 feet. So it looks like, since my y-intercept is at 0,640, that my bridge here, the extrema, the top part of it, goes up 640 feet, right? So the distance from the ground to the top of the bridge is 640 feet. So we look at our y-intercepting, it already breaks it down for us here. The graph intersects y-axis at 640, so the y-intercept is 640. This means the height of the arch is 640 feet at the center point. That's what we were concerned about. Ask yourself, what does it mean? Okay, great, I know what the intercept is, but what does that mean? We obviously know I didn't answer this one first, but this is non-linear. It's a parabola. It is not a straight line, so that's what they're saying here. Linear or non-linear, since the graph is a curve, it's not in a line, it is non-linear. Okay, and then we have our x-intercepts. So it looks here like our x-intercepts are at, what is this, 80, and this one's 240. So there's 1/6, so each of these is worth 80 as well. Okay, got it. So the next one here would be 320, negative 320, and this one over here would be positive 320. Distance in feet. I was looking at height in feet before. So what does that tell us? That the arch extends 320 feet from the center on both sides, right? Which means it's about 640 feet all the way across. So the graph intersects the x-axis here and here. That's what we just showed. So the x-intercepts are here and here. This means that the object touches the ground 320 feet to the left and right of the center. This means, that's what we're looking for. This means, what does it mean? All right, and then symmetry, that's the last thing. Does it have a line of symmetry? The right half of the graph shows, the right half of the graph is the mirror image of the left half in the y-axis. So if we drew a line right here on the y-axis and we folded this guy up along the y-axis here, both sides would match up perfectly, right? This side goes 320, this side goes 320. They would match perfectly. Oh, my tablet powering off. In the context of the situation, the symmetry of the graph tells you that the arc is symmetric. The arch is symmetric. The height of the arc is, at any distance to the right of the center, is the same as its height and the same distance to the left. If they're symmetrical, whatever happens on the right is the same as the left. So they are symmetrical. The center point would be the line of symmetry. So we'll just say yes, has symmetry, has line symmetry. Okay, then if we kind of look at these real quick here on the bottom, these graphs, it says identify each function as linear or nonlinear, interpret the intercepts, and interpret the symmetry. So we're just looking at those three things. So for this first graph, on the bottom, it's generations since 2007, generations of the right whale population. When I first read that, I skipped over the whale part, and I was like, there's been not 12 generations since 2007. That's crazy, but whales, you know, they're different than us. And then the populations on the y-axis. Okay, so if we're looking at this line, the intercepts are here. This is my x-intercept, and the y-intercept looks like it's up above 240 here. So this is about 10, and we'll say, because it goes above 240, I'm going to call that 250. If you wanted to stick with 240, you could. All right, so what does that mean? If this is 2007, because this is generations since 2007, for each of these is 2. Each little tick mark is worth 2. So this must be 0 is 2007. So 10 generations since 2007, the population of the right whales is 0. It went all the way down to 0. So we'll say 10 generations after 2007, whale pop is 0. They're done. They're extinct. There's no more whales, right? 10 generations later, it just kept going down, down, down. They weren't breeding much. They weren't making more whales. So by 10 generations later, they're all gone. Excuse me. And then the y-intercept shows 250 whales in 2007. If the y-axis represents 2007 and everything to the right is everything after 2007, then in 2007, there was about 250 whales. So we can say in 2007, about 250 whales. That's what we can interpret from this graph. And then I guess they just kind of died off and less of them were being born. So after a while, they were done. They were extinct by 10 generations after 2007. Okay, next, we didn't discuss symmetry. Is there any symmetry? If I fold this in half anywhere, will it meet up? No. So we can say no, symmetry. We can do that one first, get that out of the way here. Does it look like this is symmetrical? No, not at all. It's not mirror image. If we drew a line right here, this side has a little kink in it, this side does something completely different. So we'll say no symmetry. Linear or nonlinear. This is nonlinear. It's not a straight line. Oh, well, it's not one straight line, so it's nonlinear. It's made up of a bunch of straight lines, but the entire graph as a whole is not one straight. It's not constant. And then we have to look at the intercepts. All right, so this is about the price of stock. So on the bottom, it's time. Time is always on the x-axis. Time since the opening bell each day, opening bell stocks, and then the stock market, and then the price variation in points goes up and down the y-axis, right? So we start off when the bell rings at the beginning of the day or whatever the period is for the stocks. And then it looks like stock prices go down for a little bit, kind of sharply, and then it kind of backs off a little. It's still going down, but not as sharp. And then it goes up right away. It goes up, 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 kind of steady. And then it levels off and it just goes flat, right? So that's what we're looking at, the price of stocks, okay? So we have our intercept here, our x-intercept, and our y-intercept is at 0. So what does our x-intercept mean? Well, we can say that our y-intercept, which is at 0, 0, means at the bell, there was no variation. This isn't talking about the price of stocks. This is talking about the variation in points. How much did it change? Did the stock price go up or down? Well, it went down. How many points did it go down, right? That's what we're measuring here. Kept going down. Then it went up. The variation went up. So at right here when the bell rang, it hasn't varied at all. Right? So 0, 0 means at the bell, there was no variation. And then by the time we cross the x-axis, remember this is variation measured here. So by the time we get to about a little over 4 or 5 hours later, x-intercept, 5 hours later, there's no variation again. 5 hours, at 5 hours, exactly 5 hours, at 5 hours after bell, there's no variation. Now, the variation's steadily increasing, but at that point, there's no variation because we're at 0. Okay, and then lastly, this is definitely not linear, curvy, non-linear. Is it symmetrical? Could we fold it in half? Down a vertical line? Nope. So it's no symmetry. And then we have to look at our intercept. So this is the average price of gas. And then on the bottom, it's time, years since 1987. And on the side, it is price per gallon. So that means if it's years since 87, that 0 here is 1987. And then we have 5 years later, 10 years later, 15 years later, blah, 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 right? So for our x-intercept, we're crossing the x-axis never, none, which means the price of gas was never at 0, right? It started off in 1987 at looks like right around $1 per gallon, and then it just went up from there. It either stayed the same or it went up. So gas never at $0. Gas was never free. And then the y-intercept is right here at 1. So that means in 1987, which is year 0, gas was about $1 per gallon. I'll try to do my slash and my 1 at the same time. In 1987, gas was about $1 per gallon. That's what my y-intercept is telling me, where I touch the y-axis. So does that kind of, I hope that kind of makes sense as far as analyzing graphs and all. Oh, I have the same thing here. Oh, we were just looking at different pieces of it. We were looking at end behavior and relative extrema. We've already done that a ton, so I'm not going to do it more. It's the same exact graphs we just looked at on the front. We're just looking at different parts of it, but I'm going to stop there. So let me know if you have any questions. Thanks.